Professor Murphy. In this module, we are going to discuss how to design and create a database. These processes are actually quite complicated, and the actual design process will be addressed in a later course. This module is an introduction to some design concepts, and you will learn how to create a database and use some design tools. Before we begin, let's look a little closer at how information gets cycled. I bet you have entered your name, address, and email address in many online forms. And presumably that information goes somewhere so you can get something, right? Maybe you order a shirt, or maybe you are signing up for a new app. That process is basically a transaction, and the system that collects it is called a transaction processing system, or TPS. Most transaction processing systems collect this information and store it in a database for later use. Initially, it may be used to process your order in the case of that shirt you wanted. The database grows as many transactions occur every day. As we discussed in the last module, it is very inexpensive to store this data, and companies realize that they could learn from this history to be better in the future. Some of the techniques that look at this data are called data mining tools and techniques, such as looking for patterns in the data. For instance, that shirt you ordered may be compiled with many other transactions, and the company learns which shirts are popular in which parts of the country or at a certain time of year. The knowledge learned from these databases can be used to create new business systems and new processes, and the cycle begins again. After gathering the information we need for a database, we have to make sense of it. The data modeling techniques are used to help us understand the data and model it in a way that will allow us to easily access it later. It is much like a blueprint for a house. Most people would not build a house without a blueprint. You want to know how the house will be used and the needs of the owner, because you do not want to be done with the house and find out it's not what was needed, right? For a relational database, we use an ER model to help us understand the relationships between different data in a database. Database design focuses on one particular organization. As discussed in the last module, the most widely used data model is the relational model. It is based on a single relation called an entity. One database usually has many relations. We discussed some of the basic terminology in the last module. We discussed an instance of, but we did not discuss null. Null is an empty field. It is an attribute of a single record that does not contain a value. We also discussed the basic objects called entities, and in a database, each entity has its own table. But a database is not a set of unrelated tables. What makes the database a relational database is the connections between entities. Every table in a database should be related to at least one other table. Otherwise, it shouldn't be in the database. This concept may seem confusing, but no worries. We explore these concepts in depth in the database course. For now, it is only important that you know that a database consists of multiple related tables. For example, in our university case, students and teachers have a relationship with courses. Students enroll in courses and teachers teach these courses. Every table in a database, regardless of whether the table represents an entity or a relationship, must have one or more attributes that can uniquely identify each record. This unique identifier is called the primary key. Although you will not be learning the details of database design in this course, it is important to understand the null field because nulls can be problematic in a database. Primarily because we simply do not know what it means when a field is null. For instance, if a student has a middle name value that is empty or contains no value, it may be because the student does not have a middle name, or it could be that we simply forgot to collect and store the middle name. The primary key value cannot be null. Every instance or record of a table must have a value in the designated primary key field. Designing a database can be a long and complicated process depending on the needs of the organization. In this course, we are only going to design a very simplistic database. Regardless of the size or simplistic nature, good design is very important. Failure to follow good design principles can lead to inconsistencies in the database. These inconsistencies are called anomalies. The best way to understand what can go wrong in a bad design is to use an example. In our university case, we are simplifying the database by only using basic information and only collecting information on teachers, students, and courses. I will assign shortened names to the basic teacher, course, and student information. In our very small university, we have 3 teachers, 5 students, and 5 courses. These 3 instructors can teach more than one course, and students can take more than one course. In explaining what a database table looks like, I said that it was made up of rows and columns, much like a spreadsheet. However, spreadsheets should never, ever be used as a database. This slide represents using a spreadsheet for storing our simple database. Do you see any issues? Do you notice all the redundancies or repeated information? Every time a student enrolls in one of my courses, all my information must also be entered. Entering data requires repeatedly entering the same information over and over again. Imagine if we had 20 or 100 teachers teaching 100 or even 1,000 courses. That is a lot of repeated information. But it isn't just the tedious data entry. This repeated data entry can lead to anomalies. We have 3 basic anomalies. An update anomaly is a data inconsistency that results from data redundancy and a partial update. A delete anomaly exists when certain attributes are lost because of the deletion of other attributes. An insertion anomaly occurs when certain attributes cannot be inserted into the database without the presence of other attributes. Let's look again at our redundant table. What problems will we have if we have to make an update? For example, if a teacher changes offices, that new location must be changed for each course and each student. If I change my office location, it must be changed 10 times. The chance for error is very high and can lead to one or more records having my old location while the rest have the new. Now imagine that over time there are many updates. The chance for error is even higher, leading to many more inconsistencies to the point where none of the data can be trusted. How about a deletion? Do you see any records that may lead to problems? Look at the record with Kurt Johnson. He is teaching one class with one student, and that class is the only one taught. What happens if the student withdraws from the course? Kurt and the class information will also go away. Finally, can you look and see when an insertion anomaly may occur? Since we never know how much or what new information may be needed in the future, our design must be such that these additions would not require redesigning the database. We only want to design the database once. Many issues can occur, especially over time. This database, as designed, does not have a good mechanism to record teachers who are not currently assigned to teach a course, new students who have not yet registered, or current students who may be taking the semester off. Wouldn't it be great if all the student information were in one table, all the course information in another, and all the teachers in a third? That would eliminate all redundancies. Great, right? Well, not quite. Can you see the issue? How do we know which students are taking which classes and which teachers are teaching which courses? These examples describe the relationships between the entities. Students enroll in courses and teachers teach courses, yes? The goal is to reduce the redundancy to avoid mistakes, but still preserve the relationship. This process is called normalization. Normalization is a database design process aimed at reducing redundancies in a database and therefore increasing data integrity by reducing the chance of inconsistencies. This degree of design is beyond the scope of this course, but for now I want you to remember two things. Normalization is reducing redundancies, not eliminating redundancy. Why? Because if you eliminate all redundancy, you also eliminate the relationships, which is kind of the whole point of having a relational database. Two, the normalization process increases the likelihood that you can trust the information that you retrieve later because you have less chance of anomalies. Now, I am simplifying the university case to basic student enrollment. We know that universities, even small ones, must collect a lot more information than what we will demonstrate here. But you can trust that we will create a normalized database. Your first assignment is to complete an ER diagram. Because our case is very simple, it may be easier just to jump to creating a database, but it is important to know the process. Learning how to diagram, working with the diagramming tool, and converting the diagram to a working database will go a very long way to helping you in later courses. Your second assignment is to create and access database with 4 tables. This assignment will teach you the mechanics of creating a database. And finally, your third assignment is to use the database. You will create a form to input data, use the form to input some test data, and run a query to retrieve information. This assignment will help you understand how to use a database. Users are better designers because they have a better understanding of the data and why it is needed. I hope you enjoy your assignments. Bye for now.